In a Monte Carlo tree search, we repeat the process of selecting a leaf node, expand it, and play a row out via a random walk to the terminal state, then update the results along the node path. To apply Monte Carlo tree search, we assume the decision made in each step is under a static condition. We don't allow stop options, and we don't go backwards until the Pac-Man meets a dead end. We first start with a node corresponding to current state. Expand it to successive states, select a random node child, and do a roll out. We define the terminal state as 10 steps ahead or a crash on a ghost. Evaluate that state, then propagate the result back to the root node. In the following rounds, nodes are selected with UCB in terms of explore and exploit. Complete all iterations and limit the tree to the depth of 5. The evaluation is using these features so that the path that eats more food goes home and score and does not crash into a ghost will score higher. Challenge is to tune the features on their weights. The tree search construct a tree that is so big that it's usually hard to capture a failure moment and see which evaluation goes wrong. For pitfalls, we assume the environment is static. Thus, when a Pac-Man is being chased, it eventually gets into an alley with food rather than getting rid of the ghost. Another pitfall comes when an agent has equally good score in either direction. It tends to go back and forth repeatedly until it sees an opponent. Improvements expected is a trap recognizer. By analyzing the layout, the agents would know if there's any area on map that has only one way out. In this case, we could try to trap the opponent or avoid being trapped by a ghost.
Hi, I will talk about Pac-Man contest with reinforcement learning. First, I will introduce some design rules, then introduce features and ways, and talk about challenges and improvements. At start, one agent will be offensive and the other will be defensive. The defensive one will always patrol the borders, and the offensive one will always go for the nearest food. When action steps is less than 50, the offensive one will navigate back. Here are the features for the offensive agents, and here are the features for the defensive agents. All food and ghost related weights are gained by reinforcement learning against ghosts in Project 3. Other weights are manually adjusted. The workflow is like such. The agent will get a legal action based on its current state, then compute the score as a linear combination of features and weights, and choose the action with max score. Here's the daemon of offensive agent. The red agent spot there is no ghost across the border, so it go for the foods and get chased by ghosts, so it go back and make the deposit. And here are the daemon of defensive agent. The orange one will only patrol around the border and fail to catch a Pac-Man by merely just driving it back. The offensive one works fine, but the defensive one needs some improvements. The challenge is this is hard to debug since it is hard to play a certain situation multiple times. And also for reinforcement learning, it lacks suitable components to training on. Some improvements can be the offensive agent can be improved by optimization of the weights. And the defensive can choose a new strategy since patrol around the border doesn't really help much.
Programmed using general heuristics. The first agent in general is an offensive one but kills a nearby invader. The second agent is a semi-offensive one. By default, it goes hunting but becomes defensive when an invader is present or a specific number of defending foot is lost. Nearest foot and nearest invader gives a position and distance of nearest foot and invader respectively. Top foot, previous foot, and current foot gives a list of foot at different times. Invader POSIX and POSIX is used to store the position of last foot eaten by invader. Scared path is used to check if escape from ghost is required. Eaten gives the non-deposited foot. Escape path gives path to whom using BFS. Get a previous observation gives the details of previous games. Score evaluation is as follows. The offensive agent takes into consideration of nearest ghost more than the nearest invader. For the semi-offensive agent, we have a nearest invader known position and nearest invader predicted position, followed by nearest ghost. The rest is the same for both. Understanding weights and combining them and being adaptable to all maps were the challenges. Improvements could be design of functions that could enhance the path, putting more practical weights, and thinking from opponent's view.